Hello, my dear students, and welcome to a new chapter in our measurements and instrumentation module. Today, we are bridging between two topics. Today is the last lecture or the last chapter dealing with analog measurements. And starting from the next chapter, inshallah, we are going to go with the analog to digital converters or the ADC, which most likely will consume the remaining six chapters or the remaining 6 weeks of this module. So today we are clothing the analog portion of our course with what we can call the analog noise, or in other words, how we can analyze analog noise. If you remember my early lecture, maybe in the first lecture or the zero lecture, we considered that there is nothing called a measurement without an error. And one of the sources of the error is the noise. So noise is everywhere. What we are going to show you during this lecture is simply how to statistically analyze this noise in order to determine what we can call the noise immunity of our circuits. So let's start together this chapter under analog noise analysis. Okay, so as I just mentioned, noise already exists. The main issue or the main obstacle while considering noise is an unexpected or non-expected signal. It's not a deterministic signal that can be expressed in a function. It's a random variation where we cannot predict the value of a noise. So during this lecture, or in general, while we are dealing with noise, we have to consider what we can call the statistical analysis of the noise, which I think most of you already have passed through the communication and the communications theory. And in the communication theory, we first start with separating signals into what we can call a deterministic signal and what we can call a random signal. And whenever it comes to random signal, we have to apply statistical and probability theory in order to study random variation, which is typically what we are going to do during this chapter. Okay, so as this signal is simply a variation with respect to time, the longer period of observation, the better understanding of the noise performance. So simply, whenever we consider a variation x, which is x here represent the x of t as a function of time representing voltage, we can represent the average power of this noise signal as v squared over r, which is here x squared of t over r, with the period of the signal from negative t over 2 to t over 2. And as I just mentioned, when t tends to infinity, we can have a very accurate observation for the noise. So this is simply how we can determine the average power of a noise. In order to make life easy, usually instead of expressing this in terms of watts as v squared over r or voltage squared over r, we ignore this r impact and we write it in this way. In other words, we can say that we assuming that r equal 1, or in a different way, we can say that this is not a watt, it's more toward a voltage square unit. And this will be our standard way of monitoring the power due to noise as the voltage square with an integration where we are considering to expand the limits of this integration from negative infinity to infinity in order to have a very accurate observation for the noise. So the issue is, usually in any circuit, we have what we call processing for the signal. So we have, for example, a low-pass filter, a high-pass filter, a band-pass filter, a gaining unit with a limited frequency band, whatever it is. As your signal, your original signal is being processed, your noise is also processed in the same manner. And considering our signals and system background, we know usually that when we have a signal processing, it's much more easier to consider this processing in terms of frequency analysis rather to be in terms of time domain analysis. So for example, we say that we have an X of t signal with a low pass filter L of t. So the output is a convolution between X of t and L of t. We can say that simply the output is the multiplication of X of f and L of f, where X of f is the spectrum of the input and L of f is the spectrum of the filter. So simply the output is the multiplication of these two blocks. So herein we use X of f instead of X of t, where X of f here represents the frequency spectrum of your input. Dealing the same way with noise, instead of using the P of t or the average power or the X of t, we use what we call the probability, the power spectral density or the PSD. The power spectral density is simply what we can call the variation of the frequency component of the noise. So as you can see here we have the S of f, which is typically the Fourier transform for our noise spectrum. And here we have the f as an x-axis. And as you can see, we are mapping the variation of our frequency of our noise across different frequency component, and this is what we call the PSD. And what we usually do is that we average this spectrum to be normalized with respect to frequency, so that the PSD is the average variation of noise per frequency, resulting with V square over Hertz. Please remember that we mentioned here that the unit here is V square or voltage square. That's why we have voltage square over Hertz as a PSD unit. And this indicates what we can call the average spectral variation of our noise spectrum. Considering this, we can classify our noise based on their spectrum. And during this lecture, we can say that we are going to face two different types of noise. What we can call a frequency independent noise, or in the field of electronics, we call it white noise. The white is coming from the optical spectrum perspective, where you have something that covers all spectrums. That's why we call it white noise. So the white noise is simply a horizontal noise with respect to the spectral response or the spectral analysis. So as you can see, this noise is independent on frequency. Later on, in few slides later, we are going to face another type of noise, which we will call flickered noise, where you will find that this noise is a frequency dependent noise. So generally, we can say that we have white noise or frequency independent noise and frequency dependent noise. Again, what I mentioned to you previously is, as your signal is processed during the processing block of your circuit, your noise is processed as well. So for example, if we have a white noise that's passed through a bandpass filter, for example, this white noise will be mapped or will be shaped based on the filter shape. So after passing through the block, this noise will no longer be a white noise, and it turns to be a frequency dependent noise, because simply this multiplication process happened, which is a convolutional process in the time domain, resulting this frequency dependent spectrum. So for example, here, as you can see, we have this is a telephone system. So this is the noise associated with the voice. Once this pass through the coaxial cable of the telephone system, which with a 4 kilohertz low pass filter, because simply it's a voice filter that pass only the human voice, which is the range of 4K. As you can see, your noise spectrum affected, and it turns to be only around this 4K hertz. And the shape on the left has been changed with respect to the shape on the right due to the filter effect. Again, another important point related to the noise, which is, or maybe related to the frequency spectrum of the noise, which is the way you are mapping your noise. Because basically, we already discussed this in the previous lecture, if you remember, when we consider the frequency response, when we deal with the spectrum analyzer, if you remember this lecture, we have considered that based on that analytical theory driven by Fourier, spectrum or frequency analysis signal, frequency-based signal, are always represented in terms of an even function, which represents that we always have a signal that's mirrored around the y-axis. So as you can see here in figure A, we have a spectrum to the right and a spectrum to the left, and or what we can call the two sides of the signal. This is very famous when you deal with, for example, AM modulation with double band and single band and so on. So you have a right band and left band, or the higher band and the lower band, whatever your terminology is. So in both cases, as you can see, we usually, based on the theory of Fourier, we have to have our S of f or X of f or whatever the frequency dependent signal, we have to have it in the form of an even function. However, most likely when we are dealing with noise, because noise is not a form of an analytical deterministic function, like when we did, for example, with a delta Dirac function representing a sinusoidal, the Fourier transform of a sinusoidal. Here we are representing with more toward a probability function rather to be a deterministic function. So usually we have the shape on the right hand side where we have a single band function. So in order to make this transformation from a double side band function into a single band function, it's simply a factor of 2, because as I just mentioned, it's an even function. So 50% of the power is relocated to the right, 50% of the power is relocated to the left. So if you would like to mimic this in a single band function, what you are going to do simply is that you are going to multiply the signal to the right to represent the total power, because herein the area under the curve is a very significant parameter representing the total power of the signal. So in order to maintain the area under the curve constant with a single band or a single side representation, what you are going to do simply is that you are going to multiply the area by 2, or simply magnify the noise level, the noise spectrum by 2. This can be observed while dealing with white noise. So if you go to textbooks, you can find that sometimes when we have a single side representation for the white noise, we represent it with a parameter n, for example. And when this turns to be a double side representation, it becomes to be n over 2. So here you multiply the area by 2 when you turn from a double side representation to a single side representation. Another important way to determine to represent your noise, what we can call the probability density function, or the BDF. And if you already have passed through a probability course, you definitely know this term, which simply represents the probability of occurrence. So here representing the different state of the signal at different times, x, and here represents the number of samples, the number of repetitions, how much time this value occur. So the probability density function is a very important function that can represent for you the noise distribution of your noise. So for example, if you are considering a voltage, so the peak value for this noise is V node, and whenever you go left or right, this V node decrease in a Gaussian pattern or whatever it is. So this is the value, or this is the impact of having what we call the BDF, or the probability density function. Now let's go to another important point, which is the noise correlation. We have already represented the noise signal, but when we have sources of noise, definitely in a circuit, we will not have a single source of noise. Definitely, we will have what we can call a multiple sources of noise. But in this case, we have two classifications for these multiple sources of noise. These classification, or the two classifications, are either these noise are uncorrelated noise, so there are two different sources of noise where these two different sources are totally uncorrelated, or these sources of noise are correlated. So if these two sources of error or of noise, if these two sources of noise are correlated, and if we refer back to this equation, so instead of having x of t, it seems like we have x1 of t and x2 of t. So we can rewrite the equation in this way. So as you can see here, now it's x1 of t, which is the first source, plus x2 of t, which is the second source, all square. In order to break down this bracket, you will get x1 squared, x2 squared, and 2x1, x2, which is very important truth. Because simply, if these two parameters are not correlated, you will not face this term. The first term here is simply the average power of the source number one. And the second term here is simply the average power of source number two. So if these two sources are uncorrelated, their total power will be directly the summation of the power of the first source and the power of the second source. But once these two sources are correlated, it's not a direct summation. It becomes the power of the first source, the power of the second source, and this term, which represents the correlation factor of the overlapping of the two sources, given that they are correlated. And this can be happen here. For example, these are three different sources, which are totally uncorrelated. So when we sum these three sources together, we get a signal. As you can see, the signal by nature will not be greater than the three, because sometimes you have a voltage, a positive noise, and sometimes you have simultaneously a negative noise, so the summation might be zero. However, when you have these three sources correlated, you can see that now their summation is magnified due to this correlation term between the sources. And that's why understanding the correlation of the sources of error is something very important in order to classify either your sources of error are correlated sources or uncorrelated sources. Now let's go into circuits components. In this chapter, I'm going to limit our investigation into two important parameters which we usually face in our circuits. Usually when you are an analog designer, I think that resistance and transistors are the most common used parameters in your study. Definitely, you can extend this study to include other types of sources of error for other circuit components, and I will guide you through the e-learning with more deep analysis. However, what I can say that understanding the noise due to resistance and due to transistor may be a very good starting point in order to understand the general concept of noise. And considering that transistors are the main building block for analog as well as digital electronic circuits, understanding that noise due to a transistor is enough in order to macro scale your study to understand other types of noises. For example, if you can analyze the sources of noise due to a transistor, then you can make it for an operational amplifier, because simply an operational amplifier is a cascaded circuit of transistors acting as amplifiers. So let's start with the first part, which is resistance. The first question is why we have a noise due to resistance. This may be the initial question to be answered. Why we have noise due to resistance?